Thank you. All right, let's go ahead and make our way toward lecture 6 today, which is finishing up the Z-transform and moving on to sampling, which is kind of the heart of the course. So that's a good transition, and let's get that going. The other thing is I posted homework 3. That should be out there, and also the solutions to homework 1 and 2. They haven't been graded yet. Getting a grader to start looking at those here pretty shortly, but I guess that's where we are.
Like, is it the due date that it says on Canvas, because that's next Wednesday?
Right. I think it's way out there, the 20th. I went ahead and put it way out there. Yeah, because I think the exam is first week in November, and it covers homeworks 1 through 4.
October.
Yeah, thank you, October. Let's not get ahead of ourselves, right? We got to go through October too. So, right, we got first week in October, the exam. And so it's going to cover homeworks 1 through 4. So there's no point really to rush finishing homework 3, at least in my opinion, if we're only going to cover homeworks 1 through 4 anyway. So I guess we'll have one more assignment after 3, and then we'll kind of do a quick review and do exam. I think that's Wednesday right before, but we can look it up. When we get closer, we'll worry about what's on there. So let's finish up some of our inverse Z transform material, and I think this might be the last technique. So series expansion. So if we can take our rational expression and write it as a series, how easy can that be? Then we can just inverse Z transform each term by term. And a very simple example to make it concrete is just a simple sum of these type of terms. So as we think about it, x minus 2, z to the minus n is negative 2, so that's z squared plus x minus 1, z to the plus 1, plus when x is 0, it's just x0, z to the 0, and so on, plus . So if we could just take one of these terms each at a time, we could Z transform them into impulse functions. Pretty straightforward. So, as an example, suppose we have an expression like this: Z squared 1 minus 1/2 Z inverse, and 1 plus Z inverse, 1 minus Z inverse. So the strategy, of course, is just multiply all this out, get a series, and inverse transform them term by term. So I'm going to take this Z squared and distribute it among these two terms. So Z times 1 is Z plus 1. Z times 1 is Z minus 1. You can kind of see the reason why I did that, because then I have Z squared minus 1. And it makes this multiplication very easy. Z squared minus 1 minus 1/2 Z, what is that, minus, that's a plus 1/2. Z to the minus 1. And let's see. Now, are there any poles or anything we need to be aware of here? So you can see that if Z equals 0, no problem, no problem, no problem, problem. So it blows up. So we can't have Z equals 0. There's a pole there. Sorry about that. So inverse transforming this into the delta, or to the impulse functions, I should say. N plus 2 minus 1/2. I think that's when it's n plus 1, right? And then finally that one, plus 1/2 impulse n minus 1. So just converting those term by term, we get that. That's a pretty easy, straightforward way of doing it. But of course, why would we stop there if you can do it to any series? So let's take this to its one of its logical conclusions. Why stop at a simple algebraic expression like that when we could use the Taylor series of any function, right? So let's extend this to Taylor series, and then we'll do a peculiar example that's not a rational function, just to demonstrate the technique. So we're going to do Taylor series at some chosen point for some function f of x. So you've probably seen this before, where we start off, we want to basically approximate any function f of x at the point f of x naught. And we can do that by writing this series that basically depends on the various derivatives. 1 factorial times x minus x naught. We can think of that as raised to the first power plus f double prime at x naught over 2 factorial times x minus x naught squared, and so on, where all these are the derivatives. So that's f triple prime, or the third derivative, cubed plus dot dot dot. So you can see where this is going. We can take any function and approximate it as this infinite series of these types of functions, and now all of a sudden it's just a polynomial again. We can write this a little more compactly as just, and we'll use k of f. So the kth derivative evaluated at x naught, k factorial x minus x naught to the k. And sometimes you might have heard sometimes people use the expression, it's a Maclaurin series, if x of 0 is 0. So if this is a 0, then it's referred to as a Maclaurin series. So now let's take this, and to demonstrate the technique, let's use a interesting x of z. So you can see this one is really peculiar, since it's not a rational expression or polynomial or anything at all. And it's a good example of this because we don't need to have that to take these derivatives and evaluate it at x naught. So let's evaluate at x naught equals 0. And we're going to do an expansion. We're going to make this easy. And so we're going to expand log of 1 plus x. So f of x will be 1 plus x. We're going to do that just to make it sort of easy to get all our ducks in a row, so to speak, because we need to keep track of these derivatives and everything. So if we do that, f of x is just log of 1 plus x, no problem. F prime, well, that's easy, it's just the reciprocal of 1 plus x. I'm going to write that as 1 plus x raised to the minus 1. Double prime, can take the derivative of that, minus 1, 1 plus x to the minus 2. And we'll do one more. The third derivative. 2 times 1 plus x to the minus 3. And so on and so forth.
Why don't you do the factorial?
Because I'm just trying to get the, what I'm going to do is sort of write out this function f of x, and to do that, evaluate it at x0, and let's see, am I in the right place? Sorry about that. The reason I'm doing this is because I just want to evaluate kind of the way I wrote this out long ways, just so you can see what's happening, and I only care, I'm going to write down this expression, but I need each one of these f prime of x0s, f double prime of x0, f triple prime of x0. So I'm just writing it down to have it and to hold it, not to write yet. So this is just sort of your cheat sheet that we're going to look at when we start trying to put it all together. So let me move my cheat sheet over there. And now we're going to apply our Taylor expansion. So we've got log of 1 plus x, and that's approximately equal, because I'm just going to write down some of the terms. Log of 1 plus x, because that's the very first thing that starts off. F of x naught. Well, x naught is 0 in our case, so that makes it easy. 1 plus 0 plus, we can go back to our cheat sheet, f prime at x naught, which is 0, over 1 factorial times x minus 0. So f prime of x naught is what? 1 plus 0 raised to the minus 1 over 1 factorial times x minus 0 raised to the first power. And we can keep on adding these extra terms. So for our second derivative, go back to our cheat sheet and see, oh, that's minus 1. Minus 1 times 1 plus x. Well, x is 0, so we can put that in there. Minus 1, 1 plus 0, and that's to the minus 2 power, all over 2 factorial, x minus 0 squared. And we can also do our third one, which is the next derivative, which is what? 1 plus 0 to the minus 3, all over 3 factorial, x minus 0 cubed plus dot dot dot, and so on. We've got kind of a messy expression, so let's sort of consolidate this and simplify things and see what we have. So luckily, log of 1 plus 0 is just log of 1, which is 0, right? Not difficult. 1 plus 0 reciprocated is 1, 1 factorial is 1, so that's just x. And now we'll start to see an interesting pattern emerge as minus 1, 1 plus 0 to the minus 2 is just 1, all over 2 factorial, x minus 0 squared, so that's just going to be x squared over 2 factorial. And there's a minus there, so minus x squared over 2 factorial. The cube we see is positive, so it's 2 times 1 times x cubed over 3 factorial. Well, 3 factorial is 3, 2, 1, canceled with the 2, so you end up with just 3, right? And it's plus, so x cubed, and let's see, it's 2 factorial over 3. But 2 factorial is the same as 2. If we do the last one, or not the last one, the next one, we get 4 plus dot dot dot. So you can kind of see what is it happening. It's an increasing power of x for each term, and the sign is alternating, and the power of x is divided by that particular integer.
How did you know that x was 0, or did you just set it?
We set it to x is 0 because we're expanding it around that point.
Okay.
So it's kind of a choice that has to be, I guess, chosen to be, reflective of the particular problem. So let's just consolidate this. for the purposes of writing it as one big summation. Minus 1 to the k plus 1. X to the k all over k. So we've got our expression, but what is x? We let x be kind of a surrogate so we can manipulate this expression. So now what we really were after was what? AZ inverse. So we go back to the original problem. I thought I had it here. The original problem we cared about was 1 plus AZ inverse. So let's substitute that in and see what results. This is sort of a k equal 1 to infinity. And now x is AZ inverse, so that's AZ inverse raised to the k, all over k. Now we can see this ugly thing here is just a bunch of terms like we saw before of stuff times z raised to some power over and over again. So using the linearity property and the scaling property of z transforms, really all we have here is a to the k times z to the minus k, all these terms. Well, how do you z transform those? Well, those are just the impulse functions, right? So when we say it's a z transform pair, we're going to transfer all those individually. So minus 1 to the k plus 1, a to the k. Z to the minus k is just what? The impulse function in minus k. Inverse z transformed it all over k. So that is sort of the resulting expression. And I want to put this 6, another way of writing it, which is a little bit clearer, is this minus 1, and we'll make this n plus 1, a to the n, all over n, for n greater than or equal to 1, and 0 otherwise. And this is kind of more informative, really, when you write it this way, because why? Well, it harkens back to the thing you've probably seen before, a Taylor series expansion of log of 1 plus x, with the alternating signs and the higher powers of x. It's reflected there, which kind of makes sense, since that's what we use to inverse transform it. All right, now I guess that's our final inverse z transform. So now we're going to talk a little bit, before we finish up the z transform material, let's talk a little bit about the properties of the z transform. And this will be a fairly quick discussion because you'll notice that a lot of them are very much like the Fourier transform properties we talked about earlier. So typically you'd use these to help you when you're doing forward or inverse transforms. And like I said, they're similar to the discrete time Fourier transform properties. So to kind of make this discussion quick, I'll introduce some notation. So if we want to talk about a z transform, we'll say x of 1 is the time sequence, x1 of n, it converts to x1 of z. The region of convergence is capital R, x sub 1. And so on. Sometimes we're going to have to talk about two different sequences. So we'll need capital R, x sub 2. So probably first and foremost, linearity. And we already used that just a second ago. So if we have a sequence that can be broken apart into two sequences, x1 and x2, maybe this a doesn't need a subscript. A times x1 plus b times x2, as you'd hope, a times x1 of z plus b times x2 of z. And what about the region of convergence? It needs to be the overlapping portion of the two. And I think we talked about that earlier. You can't have you can't have one where it partially exists. It either exists or it doesn't. So region of convergence must satisfy both the regions of convergence for x1 and x2. Time shifting. Very similar to what we had before with the discrete time Fourier transform. If we have an input sequence shifted in time by n naught, remember it was e to the minus j omega naught, omega n naught times the Fourier transform. Well, this time it's z to the minus n naught x of z, which makes sense because what's z? Z is r times e to the j omega. So having that term kind of preserves it. What about the region of convergence? It's going to be the same, except, and there's an exception here we'll mention several times, for an addition or deletion. If I can spell deletion, of z equals 0 or z equals infinity. So if this ends up, it can end up perturbing the region of convergence a little bit, and we'll see, maybe not so much in this one, if this ends up canceling another term, if there's a z to the positive n in there somewhere, then it would clearly eliminate that as a 0 if there was z to the plus n naught up there. So sometimes you can end up with changing it. Let's go to multiplication. So multiplication by exponential sequence. Very important for the DTFT. And of course it has the same relationship here. Now it scales the Z transform, and the region of convergence now is also scaled by the magnitude Z naught times the original region of convergence. And we're going to do an example because that looks a little weird. It's like, how do you multiply something times the region of convergence? Well, we're going to unpack that a bit. Also, to keep in mind to help us with our example, is we're going to go ahead and say, let's let Z naught be e to the j omega naught. That's raised to the nth power. So I'm just rewriting this so you can kind of see what happens if we replace everywhere we have Z naught with e to the j omega naught n. Then we end up with what? If z is just e to the j omega in general, where this z naught is e to the j omega naught, then we end up with what? E to the j, and it's a shifted version, omega minus omega naught. So let's do an example to kind of show what do you mean by multiplication of a region of convergence? Not completely straightforward. So let's take an example where we have some x of n, which is r to the n, and we'll make it cosine omega naught n times the unit step. And for this case, we're going to say r is greater than 0. So this is a time series. It's a sequence. So don't lose control of what's going on, right? This is just a sequence. It's a unit step function. It's just telling you r is greater than 0. It's not a region of convergence or anything like that. We're not there yet. So that's just our example. So first step in this class, and probably a lot of electrical engineering classes, what happens when you see a cosine? You immediately think, would this be better expressed as a complex exponential? And that's exactly what we're going to do here. So applying Euler's formula to this, and let's see, that'll be e to the j omega naught n u of n plus, and we'll just write this way, r of n 1/2 e to the minus j omega naught n u of n. So just use Euler's to split up the cosine. Now what we're going to do is try to apply this this multiplication by an exponential sequence property. So to do that, we got to prepare the expression a bit. So let's do that. Let's group these terms together so we actually are sort of multiplying by a complex exponential. So I'm going to take the 1/2 out here. That's not a complex exponential. Take r e to the j omega naught and raise that whole thing to the nth times u of n plus, and we'll do the same thing over here. Minus j omega naught, all raised to the nth u of n. So now we've got these complex exponentials we're about to multiply. And what do we know? Well, we know u of n is one of our favorite z transforms, right? 1 over 1 minus z inverse, and the magnitude of z has got to be greater than 1. So this is the z transform we're going to use. So let's now apply the property in both cases. So we've got 1/2 omega naught n and u of n. What is that going to convert to? We're going to do it one term at a time, starting with that one. Well, luckily we know it's a linear, so first thing I can do is just put this 1/2 up here. That's good. We also know that this is going to be of the form 1 over 1 minus z inverse. But we also know that z is going to be scaled based on this property by z naught. In our case, z naught is r e to the j omega naught n. So I'm going to write down 1 minus z over, I'm just going to write z naught here to the minus 1, and we'll do it in 2 steps since I kind of ran out of room. And I guess the key point of confusion that can happen is notice how I just took the z divided by the z naught and raised it all to the minus 1. Why? Because that's the same in the form here, 1 over 1 minus z inverse. So don't get confused. Take the z by itself, scrape everything off, put z over z naught, and then put it back together, and that's what I'm doing here. It keeps you. So if we do that, omega naught raised to the nth u of n is going to convert to 1/2 1 minus, and z naught in our case is what? R e to the j omega naught. Now, what about the region of convergence? Here it was z greater than oops, yeah, z greater than 1. So what does it mean for region of convergence is magnitude of z naught times Rx. Well, the magnitude of z naught, that's just R. So the region of convergence is just going to be R times Rx. And what was Rx? That was just z greater than 1. So now it's going to be z greater than R. Multiplied R times that. So new region of convergence, z greater than R. That's, I guess I'll write it as z greater than R. So that's just the first term. So doing the same thing to the second term, so we get j omega naught, that's minus the nu of n. And it's going to be pretty similar, right? 1 minus z all over r e to the minus j omega naught. It's the inverse. And the region of convergence is going to be the same because why? The magnitude of this z naught, which is r e to the minus j omega naught, we don't care what the phase is. The magnitude is still that, so z greater than r, no difference.
Question.
Yes.
For the region of convergence, how do you draw equal sign from absolute value of z naught to r to r?
Right here,
Yeah.
I was just saying that the, I guess, the method for applying this property is that the region of convergence is sort of the scaled version, or magnitude of z naught times the old region of convergence. And that, okay, that's true as far as it goes, but it doesn't really explain how to do it in any particular case. It just says we're multiplying it, we're scaling it by the region of, we're scaling the region of convergence because we're scaling the thing in the z domain. Okay, well, how do you do that? And that's what this example was meant to show you, exactly how that works out in the wash, because the magnitude of this z naught is r, and so magnitude of r times rx. Since what is Rx? Maybe I should have wrote one thing that would have been useful if I would have put on this page is remind us all that z greater than 1, right, was our original Rx, which is right here, z greater than 1 for the unit step function. So I multiply this times magnitude of r, you end up with z greater than magnitude of r. That's the way it's done. Because if you multiplied both sides of the equation by magnitude of r, you wouldn't have done anything. Nothing really would have changed, right? You have to scale it. So that's the way it's actually scaled. I think the final way to put all this back together is what? 1/2 for 1 minus r e to the j omega naught. Z inverse. Now it's what? 1 minus r e to the minus j omega naught. Z inverse. And z is greater than r. I think, is there any other confusion factors here? Let's see. I guess going from here sometimes takes a second look because you see this is in the denominator. And so why isn't it in the denominator? Well, there's a -1, so it comes up to the numerator there. So I think that's your final expression. All right. That takes us to differentiation, which is somewhat useful because the example we're going to do, it shows you how to handle a multiple order pole for a certain case. So differentiation. And this has its analog, of course, with the discrete time Fourier transform as well. So we have n times x of n is minus z dx of z dz. And the region of convergence is the same. So nothing different. And this can be used to sort of analyze a second order pole system. Now, if you remember from last time, all the cases I've talked about for partial fraction expansion assumed one important thing was there are no multiple order poles. If you have multiple order poles, you have to do more stuff. But you can also, if you're lucky, end up looking at it like this. So suppose we go back to one of our favorites. We start with this. 1 minus AZ inverse. And magnitude of Z is greater than A. Now if we apply this differentiation, multiply it times n, what do we get? N A to the n, U of n. And that's going to transform into what? Minus Z times the derivative of 1 minus AZ inverse. I'm sort of a person who likes the product rule. I don't use the other one. So we can easily take the derivative of that. 1 minus AZ inverse, what's that, to the minus 2, and then the derivative of everything in there is just AZ to the minus 2. Is that right? So if we consolidate our terms here, move on up. Minus Z times that is positive Z. And we've got what? An AZ to the minus 2 to mess with up top. And at the bottom, 1 minus AZ inverse quantity squared. So n A to the n U of n has a Z transform. That's what? A Z to the minus 1 all over 1 minus AZ to the minus 1 quantity squared. So in this case, of course, Z is greater than A because the region of convergence didn't change. So this shows you in a case where that double pole situation can show up. And of course, conjugation, a very easy property. If we conjugate x of n, we end up with conjugate of z conjugate. And the rock is unchanged because conjugation doesn't change region of convergence. And our last one, time reversal. So with time reversal, if you time reverse and conjugate, you end up with the conjugate of the reciprocal of z conjugated. And the region of convergence now is really changed. It is now the reciprocal of the original region of convergence. And that's not real easy to see, so let's kind of unpack that. What do you mean by taking a greater than, less than statement and taking the reciprocal of it? So let's talk about that. In general, for most of our cases, if R of x, the region of convergence, usually has this type of form, right? There's this right-handed part where the magnitude of z is greater, so you think of those annuluses with things expanding out. But it could also be less than at the same time some other outer pole, and so then the sequence may be two-sided, right? If that's the case, then the rock is 1 over RL 1 over RR. And hopefully that you can kind of see that in your mind's eye. If this is very big, then when you reciprocate it, it's very small. So now Z is greater than that. But this is small, now it's larger, and Z is still between them. Question?
What is the subscript R and L denote?
It's just sort of reminding you that it's a left-handed or right-handed sequence when we, and it might not be a great notation. That's what the book uses. Many times for a right-handed sequence, you end up with magnitude of Z greater than R sub R, the big capital R reminding you it's right-handed. And I think we have a simplification too. Let's say if xn is real. So if we end up with a real sequence, then x of minus n is just x of 1 over z with the same region of convergence. It's reciprocated 1 over rx. So let's do one quick example of that just to show the nuts and bolts of that one. So let's suppose we start with one of our favorite sequences, a to the minus n, u to the minus n. So if we're looking at this, we know, what do we know? Well, we know the right-handed version of this is 1 over 1 minus a z inverse, where z is greater than a. That's from our tables. Now, if we're going to use the rule, a to the minus n, u to the minus n is then what? Well, this is a real sequence, so I can just jump to this x of 1 over z, so it's going to be 1 over 1 minus a, 1 over z, minus 1. And now it's going to be z less than 1 over a. And now let's unpack this a little bit. Where did all this come from? So we started with z greater than a. And in our case, if z is greater than some value, make a, then when we do the region of convergence after this applying this property, z is now less than 1 over the reciprocal of that. So now we were greater than a, so now we're less than 1 over a. And it may make sense to simplify this just a little further. 1 minus a, the reciprocal of 1 over z is just z. Also, if we look at the pole 0 plot real quick, there's going to be a pole when you look at this at where? Well, when z is 1 over a, right? That makes sense. 1 over a. There's our pole. And z is less than 1 over a, so that means we got to fill in this whole thing. That's the region of convergence. And if you remember, that's the way left-handed sequences work. So hopefully it's a good feeling that we applied the property right. Because what is a of n, u of n? That's a right-handed sequence. We did time reverse. We flipped it over. What do we got now? A left-handed sequence. What happened? We have a region of convergence that looks like a left-handed sequence. So everything matched up. All right, convolution. Let's talk about convolution, because this is how we get the output of linear time invariant systems. So, convolution of sequences. So if we have two sequences, we'll just call them x1 and x2 for now. And region of convergence Rx1 intersected region of convergence Rx2. So everything's somewhat straightforward, but there is one caveat to this. So one note sometimes gets lost. I think you have a homework problem that will exploit this note. So if you miss the note, you'll wonder what's going on, I think. So the region of convergence can be larger if pole 0 cancellation occurs. That's an occurs. So how would that happen? Well, if x1 of z has a pole at some position and x2 of z has a 0 at that same position, when you multiply them, that pole goes away. So it can't be part of the region of convergence anymore. And if that pole is bounding it, then in some way, then that's going to change it because it won't be there anymore. So you have to keep track of where these things are. Let's see. I think I'll just jump right to using this to analyze LTI systems here. So let's suppose we have an LTI system. Y of z, our output variable, is what? X of z, the input, times h of z, the system function, which is the z transform of the impulse response, right? And we know since that relationship, y of n is just x of n convolved with h of n. So let's compute an example where we get y of n by actually doing the z transforms and going backwards. So what we'll do is we'll start with x of n and h of n, convert to x of z, h of z, multiply them, and then inverse transform. So for our example, we'll let our impulse response be a of n, u of n. And we know what that is. That's just 1 over 1 minus a z inverse z greater than a. And we'll make an assumption. Assume a is less than 1. So system is stable. And hopefully that's not completely mysterious, because if z is greater than a, okay, there's your region of convergence. But if a is less than 1, what does that mean? From last time, hopefully, you can think, oh, that means the region of convergence contains the unit circle. If it contains the unit circle, then the frequency response exists. H of e j omega exists. If that Fourier transform exists, then h of n must be absolutely summable. Therefore, it's stable. So it's all kind of connected. All those connections are are said with that one statement. And we'll let x of n, our input sequence, there, also be a unit step with a capital A, u of n. So we end up with just a scaled 1 minus z inverse z greater than 1. So if we multiply these two together, y of z, x of z, h of z, we get what? A over 1 minus a z inverse times what? 1 minus z inverse. And then the all-important, what's the region of convergence? Well, z is greater than a is less than 1, z is greater than 1. So the overlap is z greater than 1. That's the only place where both of them exist. Now, luckily, we already know how to do this from last time, right? You see a problem like this, what do we got? We have two poles. There are not multiple poles. and we don't have any z's up here, so we don't have to check to see if the degree of the denominator is larger than the numerator, so we don't need to do any long division or anything. We can just simply do partial fraction expansion, which will say what, b1 over 1 minus az inverse plus b2. So we'll do that fairly quickly. Multiply both sides times 1 minus az inverse. Right, so we end up with that b1 plus b2 times 1 minus az inverse all over 1 minus z inverse, right? And then we'll let z inverse be 1 over a, or z equal a, right? So if we plug that in, a is 1 minus a inverse equals b1, and the other part goes away. So we'll hold on to that one and try it again. This time let's multiply this equation here by 1 minus z inverse. So we end up with what? A over 1 minus az inverse. That one cancels. b1 times 1 minus z inverse for 1 minus az inverse plus b2. And this time, let z inverse equal 1. So a over 1 minus a equals b2. So putting it all together, what was our first coefficient? A over 1 minus a inverse, and that's all over 1 minus az inverse plus a over 1 minus a, 1 minus z inverse, and we already said what? Magnitude of z had to be greater than 1. That satisfied the region of convergence for both of these. So far so good. Now we just need to do the inverse Z transform, which these are straightforward table lookups at this point. So that's what? A over 1 minus A inverse times A to the n u of n plus A over 1 minus A u of n. I think there's some more algebra that can be played around with, but that it doesn't really add much to the development there. So that's the end of the Z transform material. And now for the next little bit, we're going to be talking about chapter 4, which is the beginning of the sampling material. So we're going to kind of go a little bit slow at first. We're going to talk about some mathematical models of sampling, kind of show you a couple of derivations of things, and then we're going to jump right into, I guess, the consequences of aliasing and slowly make our way forward through A to Ds and then multi-rate signal processing. It's kind of what we're going to do over the next few lectures. So let's start. So this is chapter 4. So typically, how do we get this whole thing started? Through some sort of analog to digital conversion process, which we're going to go through a mathematical model of. But first of all, we have some continuous time signal, and we're sampling it with period t, and we're saying, you know what, the value of those samples are going to be part of my discrete time sequence. So we've got continuous time on one side, discrete time on the other. And T is our sampling period. And sometimes I'll use, I guess this is kind of notation. Fs equals 1 over T, which is the sampling frequency. And we'll also use omega s, which is just going to be 2 pi over T, or 2 pi Fs, as you please, which will be, this is hertz, and this will be radians per second. So this is how we'll describe our system. So given that, we've got a system, continuous time to discrete time, period t, and that gives us our x of n, which is the sampled versions of the continuous time signal. So what is this C/D? This is our continuous time to discrete time converter. And it's going to be idealistic because what we want to start off with is kind of more talk about the mathematics and its implications. And so we're going to neglect, if any of you studied A to D converters or any of the nonlinearities or other things that can pop up, like the linearity of the quantization steps and other circuit details, we're not going to talk about that in this class. So, ideal A to D converter. Also an important key is this operation is non-invertible. And I guess with the caveat, in general. Of course, you're familiar with the famous Nyquist sampling theorem. If you control the bandwidth going into this thing, you may be able to reproduce it. And let's see. So we cannot go backwards. And of course, what does that mean? So many input signals produce the same output. So we have to watch out for these things, which we will, as we move along through this material. So we're going to break up this thing into 2 steps. So our continuous time to discrete time, we're going to break it into 2 pieces. This is mainly to help us analyze it. And then here's our magic impulse train to discrete time. And that's where we get x of n. So here's the system we're going to analyze. And this is going to be our math model of an ideal A to D converter. So what is this S of t function? Sometimes it's called a modulator, but what it's really doing is sampling. It's really doing the sampling here. So S of t is just a bunch of samples. Dirac delta. So this is t minus n cap t, where this is that Dirac delta function that we like to use for analysis purposes. So this is the area of the Dirac delta is 1, the height is infinity. It has some interesting properties in terms of like the sifting property. So when we multiply that function times xc of t, what are we really getting? We're getting this xs of t function. So our input times our modulator, t minus nt. So we can use the properties of this delta function to help us simplify this a little bit. So the first thing we do is if we move x of t into the summation, what's going to happen? Well, right off the bat, what do you see? We have xc of t times this impulse train of t minus nt. Well, this thing is always 0 except when t equals n times capital T, in which case it's infinity, right? So everything else is 0. So right off the bat, keeping this as all possible values of t isn't really what's happening, right? xc can really be replaced with xc of n cap t. And this is the sifting property of the delta function at work here. So we end up with an expression that we can use like that. Now what does this really look like if we were trying to wrap our arms around it? Suppose we had some xc of t. So we've got some function. What does xs of t look like? So that's what minus t, 0 cap t, 2 cap t, 3 cap t, dot, 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 etc., etc. So here's our delta impulse train, and the area of each delta, which sometimes is referred to as its size, which is usually 1 without any valence on it or weight on it. But now the size is equal to the value of xc of t at that time. So this impulse train is xs of t. Now, what does the discrete time version look like? Well, we'll just try to draw the same curve. But now we're in discrete time. 3t, 2t, t, 0 minus t. And this is n, not t now. And these are impulses that represent x of n. So what's going on? What are the difference between these? So xs of t is 0 between samples. But what about xn? Xn, it's indexed by n and contains no information for the data between n in general. So that's between samples. So these are two very different functions that we're dealing with, at least in the I guess the theoretical setup of what we're going to be analyzing. Let's see. Now we've got our two functions. Let's take a look at all this from the frequency domain. What is happening in the frequency domain? So I tried to draw pictures of the time domain, but what's going on in frequency? And I think what I want to do is keep our little cartoon system that we're going to analyze. So keep this handy. This is what we're going to be analyzing, but from a frequency domain perspective. So given this, our modulator or our sampler, which is kind of doing all the hard work here. What happens if we take the continuous time Fourier transform? What is the Fourier transform of this thing? As it turns out, the Fourier transform has an interesting form. I say it's interesting because you put in a delta impulse train of delta functions, or you put in an impulse train, take the Fourier transform. What'd you get back? Another impulse train, but this time the impulse train is in frequency. And omega s is 2 pi over t. And it turns out it's not totally trivial to show that that's the case. It's not really that easy to show that. And so we're not going to delve too deeply into it, but we'll make sort of an aside, a couple of remarks on it. So this is sort of off to the side on this impulse train, just to give you a little bit of a flavor for it. So if we took the Fourier transform of an impulse train, we're saying that we're saying, believe me, it's another impulse train. So we've got our believe me relationship here. If we take the inverse Fourier transform of this thing over here, what does that look like? So I'm just going to write it down, 2 pi over t. And we've got k from negative infinity to infinity of all these delta functions in frequency domain. K omega s. Well, what is that going to look like? It turns out that it's not too hard to show, and only because of the shifting function of the delta function. And you end up with this kind of curious expression where omega s is 2 pi over t. So what's curious about that is that what we're saying is that an impulse train in time, that's kind of why I went on this rabbit hole adventure here, is to show that and this is what k equal negative infinity to infinity, or n, sorry. To show that a complex, this infinite sum of complex exponentials also results in this impulse train. And that might be nice for you to think of it that way, simply because probably in other classes you've thought if you put in an impulse, if you put in a complex exponential and take the Fourier transform, what is that? That's a peak somewhere in the frequency spectrum, right? Well, what we're saying is that each of these in, I guess, time, if you sum them all up, ends up being a sampled version, or all these impulses. Let's see, is that right? Yes. So, bottom line, you got an infinite sum, complex exponentials is an infinite pulse train. And the Fourier transform of an impulse train in time is an impulse train in frequency. And sometimes this is a useful, at least I like to think of it this way when I'm using the Fourier transform and sampling in a certain way, which we'll talk about. I usually like to think of it this way when I'm doing bandpass sampling type problems. I like to think of it as when I sample things, I am putting infinite copies all over the place. And so, let's see, we want to I think what we'll do is stop here today. And we'll pick up tomorrow and finish our kind of discussion of sampling and frequency and kind of work our way into signal reconstruction. So let's stop here. And see you next time. That did not work too well.
Yes.